Okay, I have written up already the results that we have obtained in the last class. The generalized Ehrenfest theorem, and we have obtained these two results in the last class, and I asked you to obtain this result. By the way, have you been able to obtain it, or was there any difficulty? If there is a difficulty, then we'll take up some time.
No, sir, we got it.
You got it? Okay. Well, you got it means you got it. That doesn't mean everybody got it. And therefore, if there is a necessity, do that. When we stop for a chat, at the time, if somebody has not been able to obtain it, just tell me. Okay. So effectively, this equation tells us that if there is any variable whose corresponding operator commutes with the Hamiltonian, then the left-hand side essentially means its expectation value will remain constant. ddt is the rate of change of the expectation value, and 0 essentially means that this will remain constant. So effectively, anything that remains constant, invariant in a system, is normally obtained from the generalized Ehrenfest theorem. For example, say the Hamiltonian itself obviously commutes with the Hamiltonian. So A is Hamiltonian. So what does it lead to? So suppose A is the Hamiltonian itself, then what does it lead to? Simple. That if it is, obviously it will commute, and therefore it will be, that right hand side will be 0. And the left hand side is essentially the expectation value of energy. So value of energy remains constant. So expectation value of energy remains constant. Notice classical mechanics. The classical mechanics would say that the value of energy remains constant. Energy conservation. But here it says that the expectation value of energy remains constant. Energy can fluctuate. That is the difference between classical mechanics and the conclusion that you have drawn for quantum mechanics. If we apply this equation to the specific situation of the harmonic oscillator, so consider the harmonic oscillator. For the harmonic oscillator, your potential function is half Cx square, and this is equal to half m omega naught square. Okay. So our del V del x is equal to, it will be half, will cancel off, it is m omega naught square x. Okay. So this is the relationship that we get from this equation, and therefore if we now put it, we'll find dp dt is given by this. And what does this equal? It says that, let me get some space. It said dx dt is equal to px by m. That is what was obtained. If we differentiate that again, d2x dt2 is equal to 1 by m dpx dt, and dpx dt is, we have just obtained, dpx dt is this, and therefore is equal to minus 1 by m del v del x, which we have just found to be minus 1 by m omega naught square x. This, you can see that m cancels off. It is minus omega naught square and the expectation value of x. So it is basically dx dt is exactly the same as the equation that you obtained for the simple harmonic motion. The only difference is that in case of x, we have the expectation value of x. Okay. And the solution that x will be a sinusoidal function, its derivative, which is related to the px, will be a cosinusoidal function, and all that will still be applicable. But only thing is that it will be applicable to the expectation value of x, expectation value of p. Okay. By the way, if we start a harmonic oscillator, say harmonic oscillator in the classical domain, its mental picture would be something like this. If you now pull it to say this position and release it, then you are pulling it and release it means you are releasing it at definite value of x, but at a definite value of p also, which is 0, because you are releasing it in a static position. Your momentum at that point of time is 0. What will be the equivalent, quantum equivalent of releasing oscillator at rest? So quantum equivalent of releasing at rest. Rest means essentially p is equal to 0. So if you see it's px, its expectation value is minus infinity to infinity psi star x at 0. Then here it will be the sandwich minus I h cross del x and psi x0 dx. I'll get this out, minus I h cross, and then minus infinity to infinity. It will be, well, if say you assume psi x0 is some function f of x, then I can write this will be f of x. Suppose f is a real valued function. Okay, so suppose this is real. If it is a real valued function, then psi star, I don't need to put a f star, and then I h cross has already come out, and this is del f x del x. It is clear that minus I h cross minus infinity to infinity, it will be this is nothing but a derivative. So this is nothing but this half d dx of f square x. Right? So this is f square means once it will 2 will cancel with this, and then you get exactly this. And therefore, this is nothing but minus IH comes out, so by 2, and it will be, if you integrate that, it is f square x evaluated at minus infinity and infinity. And this, since the f is a normalized function, therefore at infinity as well as minus infinity it is 0, and therefore this is 0. So it means that if we assume this function to be a real valued function, it immediately means the expectation value of px is 0. So the way to ensure that you start from rest, which is essentially the same as saying that expectation value of p equal to 0, in quantum mechanics you cannot say p equal to 0, you have to say expectation value of p is equal to 0, then all you need to do is to ensure that the fx is real. Clear? Okay, so regarding the generalized Ehrenfest theorem, that's all I wanted to say. Is there any question about this? Otherwise, I'll go to the next thing that I want to discuss here. Is there any question on the generalized Ehrenfest theorem? Effectively, any time that you need to obtain a conservation law, that has to be obtained from the generalized Ehrenfest theorem. And these two equations that you obtain are equivalent to the Hamiltonian equations that you will learn in the classical mechanics course. Only in place of x, we have as the expectation value of x. In place of p, we have got it the expectation value of momentum. That's the only difference. Okay, so you might get a feeling from here that the quantum systems behave, even though they are sort of distributed in space and distributed in values like p, but nevertheless that expectation value more or less behave similar to the behavior of the classical system. Shall we go to the next part? Okay, great. So let us go to the next part. This part will be dealing with the generalized uncertainty principle. So I will clear this out. The generalized uncertainty principle. You have learnt in the last semester, you have learned that learned the uncertainty principle related to the position and the momentum. The fact that you cannot have exact values of position and the momentum at the same time. There will be a uncertainty to when you get the product of the uncertainty in x and the uncertainty in p. But now, what we'll do is we'll obtain a generalized form of that, which means that it will not just be related to the momentum, but any two variables. So we consider any two variables, and it's possible to get a general form of uncertainty principle. And then we'll see that the uncertainty principle between x and p is essentially a conclusion out of the generalized uncertainty principle. This derivation will be a bit longish, so please pay attention. So consider a system. Consider a system in the state psi. Consider two observables, any two observables. So consider any two observables A and B. Now, you have learned in the last semester what uncertainty physically means. The uncertainty in A, so the uncertainty in A is, let us denote it by sigma A. It is nothing but the expectation value, or I will put it in the variance way, square, then it will be easier to write. Then that is A minus the expectation value of A, this squared, because this number might be positive or negative, squared, whatever you get, its expectation value. That is the uncertainty, a measure of uncertainty in the variable A. So effectively, it is related to the standard deviation in the distribution of the variable A. Now, if we have this, then we'll know that any value can be obtained from the sandwich integral. So we'll write in the bracket notation psi A minus then this operator square psi. Notice this whole thing is an operator. A is an operator corresponding to the variable A, and the expectation value of A is a number. But here in this, it is an operator, meaning that whatever this operates on, what it does is it multiplies that by a number. That's it. That's also an operator, right? So this is then, since A is a physical operator, which means that it has to be Hermitian. So a Hermitian minus another Hermitian. So the whole thing is Hermitian. A hat minus A expectation value of A is totally a Hermitian operator. So I can get it this side. So it will be A minus operating on psi. Again, A minus operating on psi. Okay. And now if I say that to simplify and shorten the notation, this whole thing I call F. F is nothing but A minus A operating on psi psi, and your G, I'll say, is similar thing for B. Operating on psi. So in that case, I can write this as simply F. And I can write similarly, I can get some space. Oh, I'll give this. Is there anything down there? Yes. So now you have similarly the uncertainty in B is given by similar things for B is written like this, G. Okay. So now we invoke the Cauchy-Schwarz inequality. If you recall, it was equality. It was F G G greater than equal to, it was F G mod square. Okay. I have not really proved the Cauchy-Schwarz inequality. I just gave a hand-waving argument with vectors, but it is easy to prove this Cauchy-Schwarz inequality. One of the tutorial problems that I will give, you will prove this. And I wanted you to be used to these bracket manipulation. So I did not deal that in the class. I am rather kept it to give you in the tutorial. So you will do that. You will get the Cauchy-Schwarz inequality. But let us today assume that this is right, and then let us proceed. Okay. Now we have seen that this I can substitute here. This I can substitute there. So this gives sigma square sigma b square. That has to be F G mod square. All right. Let us keep it. We'll come back to that. I'll call it, say, 1. I'll come back to that. Now, any complex number can be expressed in terms of its real part and imaginary part. So any complex number Z can be written as real plus I into imaginary part of Z. That also gives another inequality, because from the, this is real part of Z, the imaginary part of Z, and then this is Z, and therefore I can use a inequality Z square should be or should be equal to real part of Z square plus imaginary part of Z square. Obviously, this is bigger than only the imaginary part. Okay. Now, what is the imaginary part? Suppose our Z was, suppose A plus IB, then the conjugate is Z star is A minus IB. So if I subtract, I can see that Z minus Z star is equal to twice IB. And therefore the imaginary part can be Z minus Z star by twice I. So this can be written then as greater than equal to mod 1 by twice I, 1 by twice I, Z minus Z star, Z minus Z, this whole thing, it's mod square. And therefore this is nothing but, since this is a mod, therefore I don't need, 2 becomes 1/4 of Z star square. Okay, great. So we'll use this. There is one inequality here, there is another inequality there. We'll need both in order to proceed. Now I have assumed, I have said that this is true for any Z, and I can assume any Z. The FG The inner product of fg is also a complex number. Therefore, the same inequality will be applicable to that. So let z is equal to fg. And therefore, the z star is equal to fg star. And we have already seen that this is nothing but, if you need to change the positions of f and g, it is g. Okay. So we substitute and then we can then write. Notice that we started from here. We'll just put it here. Sigma A sigma B square is greater than equal to, it was f g square, that is equal to, now I substituted here, it is 1/4, greater than equal to 1/4 of z minus z star. Z is this, z star is that. So I can write it g minus g f square. Square was here. Okay, so I have got an inequality relating these quantities, this and that. Now explore what the right hand side really means. So let us see what the right hand side really means. Let us start with this. It is f g. Now let us go back to what f was this and g was this. So let me just write it up again. Yeah. It was A operator minus the expectation value operating on psi, and this was B operator minus expectation value of B operating on psi. Okay, now since this is a Hermitian operator, I can bring it to this side to write psi A minus expectation A, B minus expectation B. Doing all this in order to get you accustomed to these, bracket manipulation and getting this to this side and things like that, and just working out in front of you so that when you do it, you do it right. Now let us expand this. Let's expand this. A, B. So first it will be A operator, B operator. I have to be very careful about the order because there's no reason to assume that they commute. AB minus A value of B, which is a number. So A expectation value of B minus expectation value of A, expectation value of A times B operator plus expectation value of A, expectation value of B. Okay. Then I close the bracket and psi. There are 4 terms here, and by property, that means this is nothing but a big integral, psi star, then this, then psi, and this integral has all these terms, and therefore we can distribute this, and because the sum of integrals is integral of sums, we can write this as psi a hat b hat psi, first term is done, minus psi a hat b psi. Now, this is actually a number, and therefore this can be brought out. Okay, so if you allow me, I'll do that step. Okay, I'll do that step in the next stage. I'll take some time then. This closes, minus, it is psi a b at psi plus psi a b psi. Okay, just simple algebra. Now you see, what is this? This is nothing but the expectation value of a hat b hat. So we'll write expectation value of a operator, b operator. What is this? B comes to the front because it is just a number. I can take it out. And it is psi a psi, which is the expectation value of a, minus b has come out and the expectation value of a. This is a comes out because it is a number, and it is rest remains the expectation value of b. So is equal to minus a comes out, and the rest is nothing but the expectation. Okay, and the third one, ab comes out, minus a expectation value of a, expectation value of b. Why? Because these are just numbers. If these are numbers, then it is just psi with psi. So it is psi, its inner product with psi, which would be equal to 1 because this is normalized. So I can delete this and simply say that it is the rest of the stuff. This is plus, sorry. Here this is plus. Then this cancels with this, and what remains is a hat b hat minus the expectation value of b, the expectation value of a. These two are numbers, so it doesn't matter in which order we write it. Okay, so we have found what fg. We can see that similarly gf can be written similarly. We can write gf as, now I have to be careful, gf is ba minus, it doesn't matter in which order we write it because these are two numbers, so I will write it in the same way. B. Okay. We started with saying that this, right? So this is what I have to alternatively write. So I will substitute this into these positions to give a square sigma b square greater than equal to 4th. Then it was 1/4 of this, right? We have to write that correctly. 1/4. It is a B minus B A. I have completed that. It was a minus B A plus this. Oh, there was a square. And I can see that this cancels off. So it becomes even smaller. So this becomes greater than equal to 1/4 of simply A B minus B A square. Okay, now I need a little space. I'll just get some. Now you see, if you have A comma B, the commutator of these two, then we can write this as the expectation value of the commutator. So A B minus B A. Expectation value of anything is just the sandwich integral. So this can be written as psi A B B A psi completes. And since this is nothing but an integral with distributive properties, we can separate them out. Psi A B psi minus psi B A psi, and therefore you can see that AB expectation value minus BA expectation value is nothing but this, and this is what appeared here. So we can write 1/4. It is A, this will be bracket A comma B. Its commutator. The square was there. Square. Okay. Great. We are done. So this is a square term. This is a square term. This is a square term. So we can write simply sigma A, sigma B, is definitely bigger than half A B. Okay, this is the result that we are looking for. Okay, this is the result that we were looking for. This is the statement of the generalized uncertainty principle. Let me write it again up there because I have now exhausted my space, so that we can. I have already done this derivation. It will be available to you on the YouTube, so you can always read it again. So let me clear this part up and write it again so that we can discussion on that basis. So let me write the generalized uncertainty principle essentially says the sigma A, sigma B, the uncertainty product of the two variables A and B should be greater than half of the commutator between A and B, its expectation value, and the modulus. So this is the statement of the generalized uncertainty. And you can see that if you assume A to be X and B to be Px, then so suppose our A is X and suppose and is px, then we know that the commutator between x and px, this is something that you've done last year, is equal to I h cross. So if you can put it here, you will immediately find that this is I h cross, then this gives what you really need is this whole thing. So the expectation value of that x px and a mod of that, get rid of the I, and since this is h cross, therefore this will just be the h cross. Put it here, you immediately get sigma x p is equal to, or sorry, not equal to, it is greater than equal to half times this, which is x cross. This is the result for the combination of x and p. So this says have definite values of x and p, and their uncertainties product must exceed h cross by 2. This is the classical uncertainty principle that you knew of, but actually the general uncertainty principle is this, which means that in quantum mechanics you will come across many other pairs of variables which do not commute with each other. Which do not commute with each other means that there will be an expectation value, there will be a modulus of the expectation value, and therefore there will be a number here, which means that any two variables that do not commute with each other, they will, for example, you will learn, I don't know whether you have learned that in the last semester, you will learn that the angular momentum in the x direction, angular momentum in the y direction do not commute with each other. And therefore, there will be uncertainty between them. Similarly, there can be other variables in quantum mechanics which will have this uncertainty. Okay. Well, I'll stop here. Expect questions from you, because this was a bit longish, but the derivation was not a difficult thing. The steps were very clear, but a bit longish. Yeah.
Yeah, so sir, now that we have proved this, we don't really need the ninth postulate that were discussed in the first class, right?
Ninth postulate was?
Ninth postulate was that if two operators don't commute, then we can't observe them precisely at the same time.
Right.
And if they commute, then we can observe them simultaneously.
Right. That now becomes a corollary of the other postulates that we had. We can forget about this as a fifth, ninth postulate. You are right.
Okay. Also, do we have an operator for time?
Energy.
Because we know that this holds for energy and time. So how does that happen?
That will come a little later. A little later this particular question, because right now it is not yet time. Because
Sir, other than the angular momentum, linear momentum, and these and energy, all these common pairs, are there any other operator pairs that follow this rule?
Well, the common ones that you will encounter in this course are these, but there can be other things that are more subtle, which will not come in this course. So I'll not complicate those ideas. But definitely you will come across the angular momenta, you will across spin. Spin have this property.
Okay, sir.
Somebody is asking what is the difference between observable and its corresponding operator. Oh, well, that is quantum mechanics. An observable is, say, a position. Position has a value. If you define your x coordinate starts here. That means this is your 0 of the x coordinate. Then how far are you? That's a number. And therefore, x is definable as a number. Similarly, is definable as a number. So many mass times so many meters per second, a number. But when you say an operator, it means that it operates on the psi function, which is a complex number, a number that is dependent on x and t, operator that operates on psi to give another psi. Okay. And it is quite counterintuitive why there should be an operator related to a observable. But this is a assertion of quantum mechanics. There always is an operator related to an observable. And the position is just multiplication by x. The momentum operator is is cross del x, and so on and so forth. There are many other such operators. Hamiltonian operator is a combination of the momentum operator and the a function of x, which is vx. So we have a something that is a postulate of quantum mechanics, and therefore I cannot argue why it is so. Postulate, the definition of postulate is that we don't know why it is so. But if we assume that with every operator, every observable, there is an operator, then you can get everything out. Results that can be tested by experiment. So we know that our initial assumption was right. So that is how things proceed. Okay, what is the difference between an operator and observable? Observable is a number. Operator is not a number. Operator is something that you do with a function. Okay, something. Multiplying by x is an operation. Multiplying by 2 is an operation. Make it square is an operation. ddx is an operation. ddt is operation, right? So you change the function by doing something. That is an operator. Quantum mechanics asserts that every observable there is such an operator. Let's stop here. I will give the tutorial problems today, and you solve it over the weekend. And I have instructed the teaching assistants to help you out with the solutions. Remember, the tutorial is not an examination. Tutorial is your practice. But it is marked in the sense that we do check how seriously are you taking it. Sir, while taking the inner product of a function with itself, let's see what it writes. With itself, do complex conjugate or complex conjugate transpose. No. If you are talking about the function, it is just a complex conjugate. Transposition comes when we talk about matrices or vectors. I'll come to that. How all these can be done using matrices and vectors. Vectors means real like vectors, like this. I'll come to that later. And then we'll deal with the question of transposition and things like that. Presently, we are only doing complex conjugate. So whenever you are taking the inner product, the draw part, when you write a inner product of psi with psi, the bra part is a psi, ket part is a psi, and therefore when you write it as an integral, it is this psi star psi dx. The bra part is in the integral takes a complex conjugate. But in this case, in a function, there is nothing like a transpose. Clear? No, let's stop now.